Hello everyone, welcome to this session. In this session I am going to discuss about the wind velocity and power from wind. Here the wind power whatever is there, power generated from the wind, it is related to the wind velocity. And that relation, how it is related, how the variation will be taking place, all these things I am going to discuss in the session, that is the wind velocity and wind power. Here wind possesses energy by virtue of its motion. Any device capable of slowing down the mass of the moving air, like sail or propeller, like a windmill, can extract the power of the energy and convert it into a useful work. There are three factors determine the output from the wind energy converter. The first one is the wind speed, which one is very important. The second one is cross-sectional area of wind swept by rotor. The cross-sectional area of that whatever the windmill is there, which is coming across the wind. Then third one, the overall conversion efficiency of the rotor, transmission system and generator or pump. The mechanical systems what are there, their overall conversion efficiency. And here about only 1/3 of amount of air is decelerating by the rotors. Only 1/3 will be decelerating, and 60% of the available energy in the wind converts into a mechanical energy. 60% of energy will convert into mechanical energy, and well-designed blades will typically extract 70% of theoretically maximum. But losses in the gearbox, incurred in the gearbox, transmission system and generator or pump could decrease overall wind turbine efficiency to 35% or less. Okay, the 35% the overall efficiency will be there, including all the efficiencies. Then the power in the wind can be computed by using the concept of kinetics. The windmill works on the principle of converting kinetic energy of the wind to mechanical energy. Thus, the kinetic energy is given by K is equal to half mv square. In this one, m is equal to rho AV. Rho is the density of the air, A is the swept area of the rotor, and V is the velocity of the wind. And here the A is given as pi d square by 4. Okay, this d is that is a rotational diameter of the wind turbine. And here m can be, if you substitute area, this m can be we can have, that is a rho pi d square v by 4. And if you substitute this m in the kinetic energy equation, we have the energy from the wind turbine. That is available wind power Pa can be given as, that is here half, in this one 1 by 4, this multiplied if you taken the 1 by 8. Then the rho pi d square is there, and 1 v is here and v square here, then it will become say v cube. The wind power or a power from the wind whatever is that 1 by 8 rho pi d square v cube. It is directly proportional to the square of the diameter and cube of the velocity. Okay, that is the wind available energy. Then continuation this one with this, how the wind speed is varying and how the wind speed affects on the air power generation, that we are going to discuss here. Wind speed largely determines the amount of electricity generated by a turbine. Higher wind speeds generate more power because of stronger winds allow the blades to rotate faster. Faster rotation translates to more mechanical power and more electrical power from the generator. The relationship between wind speed and power for a typical wind turbine is shown in figure. This is the relationship, and this we can explain, that is, the turbines are designed to operate within a specific range of wind speed. There is a specific range of the wind speed, within that only the turbines are designed to operate. The limits of the range are known as cut-in speed and cut-out speed. The cut-in speed is the point at which the turbine can start to generate power. at which the power generation started. Between the cut-in speed and the rated speed where the maximum power is reached, the power output will be increased cubically with the speed. For example, if wind speed doubles, the power output will increase 8 times. That is here. This is the plot of that is power output to the wind speed. Okay, here up to 13 km per hour there is no power generation. And behind that 13 km per hour, that is cutting speed, behind the power generation will be starts. Up to the rated power where the maximum power production is there, up to that there is a gradually increase in the power production or with the increase of the wind speed. And at this point up to certain the 54 km per hour there is a flat, the power generation will remains constant. Behind that gradually it starts decreasing, it's decreasing, and that will be reaches at certain lower value at the cutout speed. Thus here the cutout speed is point at which the turbine must shut down to avoid the damage to the equipment. Okay, here at this point the turbine should shut down because to avoid the damage to the equipment, and that may rupture at that speed because of the overspeeding, and that is called as a cutout speed. Thus the cut-in and cutout speeds are related to the turbine design and size and are decided before construction. All these speeds, whatever cut-in and cutout speed, what are there, these are decided by considering the design and the size, okay, before the construction. And here the example for the increase of that whatever the power is given, if the wind speed doubles, the power output will be increases 8 times because of the cubical relationship. This cubical relation what makes the wind speed such an important factor for the wind power. Okay, there is a power is directly proportional to the cube of the velocity. Thus the velocity increases twice, 8 times the power will be increases. That's why it will be very much important factor the wind speed is considered while considering the wind power. Thanks for watching. If you like, share, subscribe and